that if wormholes can be made, they have to be made artificially by a very advanced civilization. We're observing highly disturbed black holes that are oscillating like that.
Kip Thorne is the theoretical physicist, Nobel laureate for the first detection of gravitational waves, a pioneer of black hole and wormhole theory, and the scientific mind who guided the Oscar-winning film Interstellar.
The astronaut would see just blackness in the sky overhead. You would see basically a ring inside which you have the universe above, outside of which you have blackness. The astronaut would get squashed by that gravitational pull.
Few rivalries in science captured the public imagination, like the legendary bets between Kip Thorne and Stephen Hawking.
Stephen and I had a bet of whether that really was a black hole. He bet it was not. In the end, I won the bet. I won all of my bets with Hawking.
In 2017, Kip Thorne won the Nobel Prize in Physics for his pivotal role in detecting gravitational waves with LIGO.
I looked at it and I thought, this is too good a signal to be true. Similar to Galileo, it was the beginning of gravitational wave astronomy.
He served as executive producer and science advisor on the Oscar-winning film Interstellar.
And I initiated this movie, Interstellar. We got Chris to join as the director. I told him, you have to abandon the laws of physics because it's just too boring. The physics is there, but I would bet 1% maximum of the audience even notices that.
Mr. Professor, it's a great honor having you here. Before we start, there on the shelf it stands proof of something special. Probably this is the proof of your bet with Stephen Hawking.
On my shelf,
I will read it.
Yeah.
Whereas Kip Thorne likes to live dangerously and believes that the evil aliens will be able to reach Earth and invade it by means of the intergalactic Einstein-Rosse bridge. And whereas Stephen Hawking believes that Kip is crazy and that no evil aliens will be able to use a wormhole to travel to Earth. If Thorne wins, Hawking will award him a unique trophy. If Hawking wins, Thorne will award him a t-shirt that say, "I'm an idiot." What was the result of that bet?
That bet was a hoax. One of my students created that bet. There was never any such bet between me and Stephen Hawking. It was a total hoax created by one of my students. It has no reality. I think Stephen has probably never seen it, but I don't know.
Do you remember any bets with Hawking?
Well, I had many bets with Hawking. I won all of my bets with Hawking.
Which bets with Hawking stuck in your mind the most?
Well, I think the most famous one was the bet over whether Cygnus X-1 was a black hole. Cygnus X-1 was way back in the early 1970s. Astronomers discovered X-rays coming from a star, which seemed to be in orbit around something very dark. And it had been already argued by Zeldovich and Novikov in Russia that that would be a possible way to discover black holes, that you would have gases pulled off of the star onto the black hole, and as it flows onto the black hole, it gets heated up by friction and emits X-rays. This was what was seen, and so Stephen and I had a bet of whether that really was a black hole or not, and he bet it was not. He said, because that was an insurance policy. If it was, then obviously it'd be a great coup for him, because he really was the foremost person who had worked on and developed the theory of black holes. And so at least he would have some consolation if if it failed to be a black hole. In the end, I won the bet.
I remember also your bet about so-called naked black hole. What naked black hole is?
Naked singularity.
Naked singularity, right.
Yeah, so In general relativity, there is the possibility of a region where space and time are so greatly warped that the laws of physics as we know them fail. General relativity's laws fail due to quantum effects. And some new set of physical laws control that region. Those are believed to be the laws of quantum gravity, which are not yet well understood. But such a region is called a singularity, where the curvature or the warping of space and time is an enormously large, formally, mathematically, infinitely large warping. And a naked singularity is one that can be seen from the outside. You would be able to go in and look in and see what's going on in the vicinity of that singularity. There was a lot of evidence and speculation by Roger Penrose, and a lot of evidence that it was correct, that there are no naked singularities in the universe. That was a bet just with Stephen Hawking, between Stephen Hawking and me. And I argued that naked singularities can be formed, and he argued that they cannot be formed. And in fact, and I guess John Prescott and I were on the same side against Hawking on this. And in fact, it was discovered through computer simulations and then very formal mathematical proof by Demetrius Christodoulou that in fact you can form naked singularities, but it appears in order to do it you have to very finely tune the implosion that creates the singularity. If you perturb it ever so slightly, then the singularity doesn't form. And in the real universe there are always perturbations. So although a very advanced civilization might be able to carefully tune an implosion to make a naked singularity, in the real universe, if you don't have an advanced civilization controlling it, then such singularities wouldn't form. That's the bottom line as we best understand it today. But anyway, Hawking lost the bet because there was, as I say, initially a computer simulation by Matthew Choptuik, and then a formal mathematical proof by Demetrius Christodoulou that yes, you can make a naked singularity if you are a very advanced civilization and you do it just right.
Do you think that gravitational waves or cosmic micro background help us answer the question if naked singularity really exists?
I don't know. I doubt it. But what I think the question that can be answered is the details of the singularity and the birth of our universe. That's a different kind of singularity. And there I expect that it is true that gravitational waves produced in the birth of the universe will carry information about the birth of the universe. We one day will be able to see the waves and extract that information and learn thereby about the singularity at the birth of the universe and learn about the laws of quantum gravity that control the birth of the universe. The thing that makes it possible for this to happen is that we think that in the very early universe, the universe was expanded exponentially rapidly, exceedingly rapidly. And the expanding space in those early moments was able to take whatever came off of the Big Bang, whatever gravitational waves came off of the Big Bang, and amplify them so they become strong enough for us to see. They they swallow energy from the expansion of the universe.
In 2017, you received a Nobel Prize for observing gravitational waves using LIGO. What LIGO is?
LIGO is a set of detectors, we call them, or interferometers, that observe gravitational waves coming in from the distant universe. LIGO has created a new way of doing astronomy. We call it gravitational wave astronomy. And the point is this, that according to the laws of physics, there are only two types of waves that can be created in the distant universe, travel across the universe, bringing us information about what's very far away. Electromagnetic waves, which includes light, X-rays, gamma rays, radio waves, infrared, and so forth. So electromagnetic waves and gravitational waves. It's the only other type of wave. Gravitational wave is very different from electromagnetic wave. It is, according to the laws of physics, it travels at the same speed as the electromagnetic waves. But instead of pushing electric charges back and forth, it stretches and squeezes everything that it passes through. And so you see the gravitational wave through this stretching and squeezing. And we understood this very well back in the 1960s, when Ray Weiss and I both started thinking about gravitational waves and their detection. It was an issue of finding a design for a gravitational wave detector that had a real possibility of success. Ray Weiss came up with that design, including a lot of details that explained how to control the various kinds of noise you would have to deal with. Came up with that design in 1972, and then I joined together with him, and we, in the end, more than 1,000 other physicists joined in on this project. And we worked from then until 2015, and finally saw the gravitational waves with this detector that he had invented.
Do you remember the moment when you observed gravitational wave for the first time?
I remember when I was informed of this. It was the detectors in an automated computer system that made the first observation. And the automated computer system collected the data and organized them in a way that we could see what the waves looked like, and we could directly see that this was probably waves from two black holes colliding. And I woke up that morning. There was an email from a young colleague of mine saying, go look at a certain internal website for our project. We may have discovered gravitational waves.
What did you feel?
I looked at it and I thought, this is too good a signal to be true. It was probably injected as part of testing the system. So I emailed the young friend back and said, I think this is a blind injection. They would apply electrical forces to the mirrors in this LIGO detector that were moved by gravity waves. They would move them with electrical forces and then look to see whether they saw in the data analysis, whether they saw that motion. And so I said, it's a blind injection that the experimenters put in. He said, no, I'm on the committee of 3 people who do blind injections. We didn't do it. And we weren't doing it because we were not yet in search mode. The team was tuning up very advanced detectors in preparation for starting a search, but the search was still several days away. It wasn't supposed to start yet. And the signal came in while the detectors were being tuned, so it wasn't a blind injection. When he told me that, I still was very cautious, and I said, well, let's wait until the best experts on the team have analyzed all of the the extra noise channels where you can see all kinds of noise and understand the noise. Let's wait until we completely understand the noise that was going on at the time of the detection, and then I'll believe it.
How it changed our understanding of the universe?
It was the opening up of this second way of exploring the universe. It was the beginning of gravitational wave astronomy. It was similar to Galileo building a small optical telescope and pointing it at Jupiter and saying Jupiter's 4 largest moons, and thereby starting instrument-based electromagnetic astronomy. It was basically similar to what Galileo did. When you look at the huge changes in our understanding of the universe that followed from the technology that Galileo was the first to use for exploring the universe with telescopes, you can appreciate that now that you have this other way of observing the universe that sees aspects of the universe that can never be seen with ordinary telescopes, that's going to have a huge impact on our understanding of the universe over the coming decades and centuries. So how does it change things? It changed it by suddenly making it possible for us to begin the process of exploring the universe in this new way.
Can this cosmic wave reveal what was before the Big Bang?
It may be that by observing the gravitational waves from the Big Bang, that will give us information about what came before the Big Bang. I don't know. We have never, until now, had a tool, a way to observe the Big Bang, because all other forms of radiation, they're electromagnetic. Whether it's light or X-rays or radio waves or gamma rays, doesn't matter. They cannot travel through the very hot and very dense matter of the early universe. So with electromagnetic waves, you cannot see what was going on in the universe earlier than when the universe was about 200,000 years old. And so that first 200,000 years we don't have direct observations of. You get some indirect information by looking at the abundances of elements that were formed in the early universe. These are relic fossils, and so there are fossils like this that can give us indirect universe information, but even that only goes back to when the universe was about a minute old, and not back earlier than that. The only way to actually observe back to the earliest seconds of the universe and fractions of a second and all the way back is gravitational waves, because they're the only thing that penetrates so effectively through that hot, dense matter that it can bring us the information from the birth of the universe. So it's our big hope for understanding the birth of our universe. And the birth of our universe, we do believe, is controlled by the laws of quantum gravity, which we do not understand well. There's some understanding. But my hope is that when we see the gravitational waves from the birth of the universe, they're called primordial gravitational waves. When we see them, they will have information that helps us to understand the birth, both the birth of the universe and the laws of quantum gravity that control the birth. And perhaps then we will have the tools to begin to understand what came before the Big Bang.
In your opinion, was the Big Bang the true beginning of everything?
I don't know. I don't have...
Nobody knows, but, what do you feel?
I am a very observationally grounded theoretical physicist. I don't have strong views on issues that are far from our current ability to get the answers. And so I have no... I'm open to to various possibilities.
Maybe your gravitational waves let us find a proof existence something before.
Well, they may turn out to be the tool that breaks through, the breakthrough tool that enables us to get the answers. But that is not, we have not yet seen those primordial gravitational waves, and so I'm just waiting.
Is any question about a black hole that keep you awake at night?
No, I don't get kept awake at night by anything. But the question that is of greatest interest to me is the question we've talked about, not about black holes, but the question about the birth of the universe and the gravitational waves from the birth of the universe.
If you could find just only one question about the universe, it would be the question about the beginning of everything.
Yes, that's the most important one.
Hypothetically, when astronaut would stop exactly above the horizon of even, but didn't fall inside there, what would see?
If the astronaut stops directly above the horizon, the astronaut is feeling a gravitational pull that is enormously large. The astronaut would get squashed by that gravitational pull. He wouldn't survive very long. Now, if you ask what the astronaut would see, the astronaut would see just blackness below himself and the sky overhead. He would see basically a ring inside which you have the universe above, and outside of which you have blackness, which is the blackness of the black hole below him.
What astronaut would see if fell inside there? Theoretically, of course.
You see the answer in the movie Interstellar.
Yeah.
Cooper in the movie Interstellar, near the end, he goes inside the black hole Gargantua. And he says, as he's crossing the horizon, he says, I'm crossing the event horizon. He says that, and the camera then points up, and for just a very short time, about 1 second or a fraction of a second, you see the sky overhead, and the entire universe is inside a circle, and it's all black around. But he sees the whole external universe and the light coming in from it inside a circle above him.
Why did the ring in the black hole wrap around it and glow in the Interstellar movie?
Well, all the glowing that you see was from the light emitted by the hot disk that is in orbit around the black hole. We call it the accretion disk. It's gas that has been torn off of a star that was torn apart as it came close to the black hole. And that disk forms the disk is rather like the rings of Saturn, that it glows brightly. It's in the movie Interstellar, it is at about the same temperature as the sun is at. And it's shining brightly like the sun does. And then due to what's called gravitational lens effect, the bending of light rays by the gravitational pull of the black hole, the disk is distorted so that it looks, so that when Cooper goes inside the black hole, it looks like a ring above himself.
And
with
they're
the whole
smaller,
universe
smaller, and
inside.
smaller.
It'll get smaller and smaller, but our external universe is inside the ring. When he's inside the black hole, when he's outside the black hole appears to be inside of the ring.
Does the new data from gravitational waves detector suggest to you what we should change in that black hole vision from Interstellar, you know?
No. What the new data from gravitational wave detectors does is it is telling us about how black holes behave when they collide, and about the the dynamical warping of space and time, the storm, I like to call it, the storm in the shape of space, the storm in the rate of flow of time that is produced when the black holes collide. So it's a much more interesting behavior than you see in the movie Interstellar. But Interstellar is dealing with a quiescent black hole, a black hole that is quiet, it's not disturbed. And so with our gravitational wave detectors, we're observing highly disturbed black holes that are oscillating like that and in wild sorts of ways. And, it's much more interesting.
Yeah, my question is, do we know more how black hole look like?
We know a lot about how black holes look when they are disturbed.
Okay,
That's
more.
We know far more, but we know that from the computer simulations of black hole collisions, where the predictions are verified by the gravitational wave observations. So the gravitational wave observations, they see the waves that are produced by these oscillations of the black holes as they collide. But the details of the dynamical distortions, the details of the storms in the fabric of space and time, we see the details in from computer simulations, and then simply verify that those predicted details are right by seeing the gravitational waves.
Can we use modern physics, gravitational waves, to create receipts for a small little black hole in the lab?
In order to produce gravitational waves that are strong enough for us to see, you have to have a mass that is very big. And now small black holes can have that kind of a mass. If you had a small black hole in the laboratory, it would just fall in the Earth's gravitational field and go into the Earth. And if it was moving slowly enough, it would just oscillate back and forth through the interior of the Earth. It's not going to sit in the lab. There's no way to hold it in the lab. And its motions are slow enough that it's not going to produce gravitational waves in the frequency bands of our gravity wave detectors. And the probability that there is any black hole of that size in there is extremely small.
But theoretically, it could be possible, theoretically.
So I've not thought about this in a long time, but I think all I can say is it's extremely unlikely, but it's so many decades since I've thought about this particular issue that I shouldn't comment beyond that. I leave it to my younger colleagues who've been thinking about it more recently. I haven't thought about it in a long, long time.
A few weeks ago, I talked to Polish physicist Nikodem Popławski about his controversial thesis that black holes lead to another universe. Don't you think that such controversial theses expose physics to the charge of being unfalsifiable?
No, I don't. There are portions of the universe that we cannot observe in our epoch and with any technology that we might have. But we do know now enough about the laws of physics, and we have the possibility for better and better and better tests of the laws of physics. And we have that, and we have the ability through computer simulations to come to a firm understanding of what those laws of physics predict. And so we can get answers as to what is predicted. If we chose to, we could go inside a black hole and see what happens to us. Of course, we can't publish our results. We can't send them back out. But nevertheless, the fact that it would be possible for me to learn what's going on in there by going inside the black hole. The fact that we are getting such a good understanding of the laws of physics that we can begin to make firm predictions, I would call that verifiability. If that's not verifiability, then it's impossible to verify things. Yes, I would agree, but I find that very satisfying if we understand the laws of physics well enough to make a firm prediction. And those laws of physics, as we understand them, are capable of explaining everything that we observe, that we do observe.
What is the white hole?
A white hole is a conjectured object that instead of being formed by stuff that falls into it, as a black hole is, it is a place that begins with a singularity, a naked singularity, that explodes and matter comes out. So it's sort of like a black hole being born by a collapse of a star with time reversed. So you begin with a naked singularity, and the naked singularity spews matter out. It can be thought of as a piece of the Big Bang singularity at the beginning of the universe that didn't go bang when it was supposed to. It didn't go bang when the rest of the universe went bang. And it remained as a singularity for some time and only later exploded.
I think that the question is if the white hole is a necessary partner of black hole in the multiverse scenario.
We don't know, but what we do know is that, and this was proved by a postdoctoral student of mine many years ago, that we do know that if you have a white hole and you have matter in the universe in the vicinity, it will fall onto the white hole and convert the white hole into a black hole. It will build a black hole around the white hole. So when the white hole goes bang, the stuff it spews out can't get into our universe because there's a black hole horizon around it. Doug Airdley, who's now a professor at the University of California at Santa Barbara, he proved this in a very elegant and rather simple mathematical way with Einstein's laws of general relativity.
If we can do something to study wormhole today, if we can do something, if we have any tools to answer for some questions about the wormholes, or that's only theoretical work.
It's theoretical work because we don't have the technology to be able to try to make them. We don't know whether they can be made. We do know that our technology is far too puny, too weak to be able to make them if they can be made.
Today it is only fiction.
So I wouldn't call it only fiction. It is something that is beyond our technological capabilities. That doesn't make it fiction. I mean, traveling to Alpha Centauri is beyond our technical capabilities, but I have no doubt that Alpha Centauri is still there.
Mystery of black matter. Do we know more? Can we use also gravitational waves to get more information about that mystery, probably one of the biggest in the modern cosmology?
I don't know whether gravitational waves will give us any information about it or not. This dark matter itself, well, it doesn't matter what whatever it is made from, it is capable of producing gravitational waves. But and so there is some hope that you may see gravitational waves from objects made from dark matter. And there are various speculations about this possibility. But we do not have any, I think, any reliable understanding of
black matter,
of dark matter and of how it might produce how it produces gravitational waves. My guess is it probably does not produce gravitational waves that are strong enough for us to see, but that's just a guess.
Maybe dark matter doesn't exist.
Well, there is something exists that is producing gravity, and so dark matter is a name we give to whatever may be the source of whatever is the source of the gravity that we observe. You see its effects through the gravitational interactions of galaxies and clusters of galaxies, through the motions of stars around galaxies. You see that there is something there that is pulling gravitationally, that we don't see any light coming from it, and so we call it dark matter, and our colleagues search hard to try to figure out what it is, try to see it, but something surely exists there that is producing this gravitational pull.
There is a lot of controversial hypotheses in the cosmology, I think, today. Is it a proof that we are living in the era of the biggest crisis of the cosmology?
No. Why?
We have so many questions and not so many answers, I think.
Well, I think we have gotten a lot of answers. If you compare our understanding of cosmology in 1930 with what we have now, we have learned an enormous amount about the universe. We have learned about the existence of the cosmic microwave background, and it has become a very powerful tool for learning about the early universe. We have observations of that and of the evolution of very young galaxies and their growth in the early parts of the universe, which tell us ever so much about how the universe came to be as it is. Yes, we have huge numbers of questions, but that inevitably happens when you start to get answers. That means that you're in a domain where you then can ask more and more questions. And so I don't agree. I don't think we're in a crisis. I think we're in a very exciting phase where we will find further answers to the new questions that are opened up by the new observations. But I wouldn't call it a crisis. I know there are many people who do.
Did any new physics effects appear during Interstellar production that nobody expected?
No, but what we did do is the computer programs that were devised by Oliver James at DNEG, the Double Negative Visual Effects team, they became very powerful tools for studying new physics. So the new physics didn't show up in the movies, in the movie Interstellar, but once these computer codes had been conceived and developed, they enabled us to then see details of this gravitational lensing, details of formation of images, distortion of images, merging of images, breaking images apart that occur around a black hole as the camera moves around the black hole, and you see really quite startling kinds of behaviors of images. And we got really some marvelous simulations that show precisely how light behaves, and then we're able to verify theory associated with that called the theory of caustics.
Is it true that working on Interstellar you set Christopher Nolan to conditions, no violations of the physics law and any speculations, so should be fully compliant with science?
I proposed that this should be the guiding rules, and he agreed to them as so long as they did not get in the way of making a good movie. And so, of course, I was a little worried that he would violate them in order to make a good movie. He was worried that I would play a role of a policeman, telling him what he could do and what he couldn't do. But after about an hour or two of conversation, it became clear that we were going to work together very effectively, and it would not be difficult to reach agreement on things. And so did come one point where I told him, you have to abandon the laws of physics when you depict the trip through the wormhole, because it's just too boring. And so we talked about in what way would he abandon the strict predictions. And so that's the one place where I told him, yes, I propose that you abandon our guidelines. In all other cases, we found ways to make a great movie, a very interesting movie, which stayed within those guidelines.
And probably you spent 2 weeks trying to enforce him to throw our idea of faster than light flight.
Yeah. Well, but we reached agreement. No, the issue was I didn't spend 2 weeks trying to enforce him. He had learned by then that I should go do a real calculation to be absolutely sure. But in this particular case, I told him I didn't have to do a real calculation, and but he gave me a week. I think it was 1 week, but to think about it further, and then we had a further discussion, and so he agreed that we would not use faster than light travel.
Which wild film idea could make it to the screen today under our actual knowledge about the reality, about physics, how the universe works?
Well, I think there are a variety of things. There are really a huge number of amazing phenomena that we see in the universe. And of course, there are a lot of things that do make it to the screen. But I think issues in the birth of the universe, issues in the collisions of black holes, which have not made it to the Hollywood screen yet. They almost certainly will.
Maybe you should do this.
Yeah. I have other things, maybe 20 years from now, after I finish the other projects I'm working on.
By the way, why you decided to cooperate with Nolan?
I watched, Linda Obst and I initiated this movie, Interstellar, and she brought Christopher Nolan on board to direct the movie. So he decided to cooperate with us on a movie that we had already started, but he was the very best choice we could possibly have had to do this movie with. He brought so much of his own to the movie that went well beyond what Linda and I had conceived. We conceived the movie, then Steven Spielberg oversaw it in the early creative phase, the initial screenwriting phase, and she and Linda and Steven brought Christopher Nolan's brother, Jonathan Nolan, on board to write the screenplay. And we went through 3 drafts of the screenplay with Jonathan Nolan, and then Spielberg dropped out, and we got Chris to join in as the director. And Chris was just fabulous on this film. Spielberg said to us that we got the right director for this movie, and we really did. Steven had done science fiction movies before. His heart was not in this movie the way that Nolan's heart was in this movie. He was not just totally consumed by it the way Nolan was. And Nolan just made a fabulous movie. I mean, it's I just in this last week, there has New York Times has done and identified the 10 best movies. I've forgotten of over how many years, and Interstellar is one of them.
Which simplification of the physics?
You mean in Interstellar?
In Interstellar, yeah.
Yeah. I didn't worry about any simplification of physics. The physics is all there, but much of it is hidden, and you have to dig very deep to see it. So let me give you an example. To get in this film, to get to Miller's planet, which is the water planet that is very close to the horizon of the black hole Gargantua, that is to get there, the only way to get there is to do gravitational slingshot around a small black hole. There's no other way to slow down enough as you approach the planet. The only way to do it is by gravity. In the movie, Christopher Nolan and I discussed, well, how do we handle the slingshot issue? And we agreed that one thing is to get the idea of this gravitational slingshot into the movie very early on, and so you see a gravitational slingshot is used to get the Cooper and the Endurance spacecraft to the vicinity of Jupiter. Doing a slingshot, I've forgotten, or I think it's around Mercury, around Venus, or around Mars. I don't remember which one. So the idea of the slingshot is in the movie early on. And then when they get to the vicinity of Gargantua, Romilly, who's the physicist who's on this trip along with Cooper, Romilly makes a remark about we can do a slingshot around that neutron star in order to get to Miller's planet. Now, in reality, you need to do a slingshot around a black hole to get to Miller's planet. The neutron star won't quite do it. But Christopher Nolan didn't want to confuse the audience by having an extra black hole there at that point, because the black hole was just a very new thing in the film at that moment. And so we agreed he would use a slingshot around a neutron star. But in there is the idea, Romilly makes it very clear, using a slingshot basically to slow down as you near the planet. The physics is there, but I would bet 1% maximum of the audience even notices that. But that's the character of Christopher Nolan's films. They're filled with just a great richness of ideas that have all been put there very carefully, so that if you go to see the film 5 times, you learn something new still on the 5th time or the 6th time or the 7th time.
Do you know how many days passed since the premiere of Interstellar on Miller's planet?
Well,
I know.
Till
now.
Till now, it's a little over 1 day.
1 day and 31 minutes.
Okay, yeah.
I have a very interesting question to you. The water planet Miller has big tsunami waves. Could the black hole's gravity really create such a high walls of water?
So it's not being created by the gravity of the, it's a very indirect process. So the issue is that the planet is close enough to the black hole Gargantua, and the black hole Gargantua has just the right mass to deform the planet somewhat, so it's sort of like this.
Yeah.
It's not round. And Then the pull of the gravitational pull of Gargantua on the planet causes the planet to want to face the Gargantua. It's elongated pointing toward Gargantua. But in terms of planetary time, it's not been very long, maybe only a few months since the planet got into the vicinity of our Gargantua. So it's not yet pointing directly there. It's swinging back and forth and slowly slowing down. So it's like a pendulum swinging, and the swing of the pendulum dies out due to friction. The planet is swinging back and forth like this under the gravitational pull of Gargantua. And as it swings, the water sloshes on the planet, and it forms these waves.
It's amazing that you remember any single details of that production.
Well, these details are fundamental physics, and it's the fundamental physics that underlies the movie. And this was all done very carefully so that the numbers all work out. The other thing about this is that the swinging period, which you can calculate, you choose the mass of Gargantua such that the planet is mildly deformed. But then the swinging period turns out to be about an hour, and that's the interval between the waves on the planet. You see two waves, and they're separated by about 1 hour.
In the plot of Interstellar, I think the time difference it's enormous. Is there a realistic mission scenario in which astronauts would return to Earth decades younger than their peers?
Well, I mean, if you had adequate technology, this could be a realistic thing, but we don't have anything like the technology that would be required, nor do we have any black holes with the required mass. You have to have a black hole with a mass that is big enough that they don't get torn apart when they're that close to the black hole, that the astronauts don't get torn apart.
Is it true that when Carl Sagan was writing a novel, Contact, he repeatedly asked you for an idea of realistic cosmic tunnel?
What he asked me for was this, that he said he had in his novel, he had his heroine, Eleanor Arroway is the name of the heroine in the movie and in the novel. He had Eleanor Arroway go through a black hole to get to the vicinity of the star Vega. And I told him that you can't do that. You can't go through a black hole and come out the other side. And so I suggested to him he should use a wormhole. And so that's really, I think, the first use of a wormhole in science fiction films, as far as I'm aware. But it was as a substitute for a black hole, which is what he was originally using.
Do you believe that there somewhere can exist passenger that travel using wormhole?
I am fairly sure that if wormholes can be made, they have to be made artificially by a very advanced civilization. They don't occur naturally in the universe. And so then it's a question of whether or not there are very advanced civilizations with the adequate technology to make them. I don't know whether that's true or not. But we also don't know whether the laws of physics even permit wormholes. And it's an interesting physics question that there's been a lot of work done on it, but there's been no firm answer.
Could you really send a message from inside a black hole like Cooper did taught his daughter's watch?
So let me begin answering that by saying that early in my discussions about this movie with Christopher Nolan, he told me he wanted to have an ending for the movie that was very mysterious. even more mysterious than the ending of the movie 2001: A Space Odyssey, Stanley Kubrick's great film. And so he does. It's very hard to understand the ending of the movie. And later on, when I decided I would write a book about the movie, we agreed that I would explain it in the book, but that's the only place you'll ever understand the ending of the movie. So he's not sending a message from inside a black hole. What happens is when he falls into the black hole, as he gets very close to the, quote, gentle singularity, it's called that by Romilly, he is captured by a spacecraft called the tesseract, which travels in the fifth dimension. So it's a spacecraft with 4 space dimensions. And it has the 3 space dimensions of our universe, plus the fifth dimension of the 4th space dimension of the bulk. And he's carried by that spacecraft into the bulk, into the higher dimension, into the 5th dimension, it's called in the movie, and carried back to Earth. And although the distance back to Earth in our universe is billions of light years, the distance back to Earth in the bulk is far less. It's less than the distance between the Earth and the Sun. He's able to get back in just a few minutes, and then the spacecraft docks beside his daughter's bedroom in the 5th dimension. Yeah. And all of the action that you see in the last part of the movie
of the Interstellar movie, right?
In the last part of the movie, everything is happening. He's right there by his daughter's bedroom and sending signals to his daughter.
Firstly, I thought that this is the metaphor of the hypothesis of infinite copies of us, you know. And later I understood the division. Could a wormhole near Saturn form naturally in space?
No, we don't. We're almost certain that wormholes cannot form naturally in space ever. If they exist, they have to be made by a very advanced civilization.
Which moment from Interstellar production do you remember the most? One single moment.
I would say the moment where Cooper plunges into the black hole, and where you see him plunge into the black hole, go through the horizon, turn around and look back and see the universe above him. I mean, this is how the computer simulations show what he would see, and you actually see that there.
You discovered a new star, kind of stars, with Polish scientists, right?
Yes. Well, yes.
Could you tell me something more?
So the Polish scientist was Anna Zhetkov. She was a student of Bogdan Paczynski, who was one of the really great astrophysicists of the 20th century. And so I had been working primarily in relativity theory up to and I wanted to work on some more realistic astrophysical project. And I met Anna, I think, at a conference in Cambridge, England. And I think Bogdan had probably suggested this problem to her, could you have a star that has at its center, it has a neutron star in the interior. So there's a core of the star that's a neutron star that has densities like an atomic nucleus, has a size of a few kilometers. Then it's surrounded by an envelope that is really big. What would such a star look like? How could such a star form? It was basically called a star with a neutron star core in it. And so she invited me to work with her on that project because I knew relativity very deeply, and relativity was involved in this case because the neutron star has such strong gravity. And she knew a lot of astrophysics, what she had learned from Bogdan. And so we combined forces with her knowledge of astrophysics and my knowledge of relativity. And so I taught her relativity, she taught me astrophysics, and we analyzed the problem.
And you combined.
Combined, and we figured out what such a star should look like. These are now called Thorne-Zhitkov objects, after my name and hers. And
Thorne-Zhitkov objects,
yes,
right?
TZOs.
Yeah.
And people are searching for them. There are candidate TZOs, but no firm discovery of one.
What are you doing now? Tell me something about your actual study.
Well, so I am 85 years old, and 16 years ago I made a decision to resign from my professorship and start a new career. So I made the gradual transition into the new career. The point was that I'd been a conventional professor for nearly 50 years, and I thought for my next 50 years I wanted to do other things. And so I made this gradual transition to where much of my career is collaboration with people in the arts, and working on projects that basically communicate ideas, deep ideas about science through the arts. By the arts, I mean film, so Interstellar. Painting, I have a book of my poetry and paintings by Leah Halloran, a superb young painter, about the warped side of our universe. And we basically have tried to invent a new way to communicate the essence of ideas about warped space-time to non-scientists. The new method, the new tool is tightly integrated, tightly coupled paintings and verse or poetry. And so that's another project. I've done several multimedia concerts with the composer Hans Zimmer and the visual effects team at Double Negative at DNEG, where the visual effects team, Paul Franklin and Oliver James and colleagues, have edited videos that are made by astrophysicists about the universe to fit Hans Zimmer's music. And we do a concert where the orchestra plays Hans Zimmer's music, videos from astrophysicists made much more beautiful and edited to fit the music go across the screen. And then we stop after a prologue and we talk about the music, about the science that you're seeing on the screen, about the making of the videos, and then go on. So I've done that kind of a project. I'm thinking of writing a novel, and so I'm basically enjoying myself doing those. But actually, for the last few years, most of my time has been going into writing a history of the LIGO project, this gravitational wave project.
Do arts inspire you stronger, deeper than physics?
No, but they inspire me greatly, and the combination I find to be very powerful and a wonderful opportunity to be creative in different ways. And and I find my collaboration with artists, artists said broadly, artists including filmmakers, musicians, painters, and so forth, I find those collaborations to be very interesting, very fulfilling, because they are so creating themselves, And they can ask questions of me that make me think deeply about things I wouldn't have thought about otherwise.
Have you ever asked yourself why science? Why you are scientists?
No, I'm a scientist because very early on I discovered that science has enormous power for explaining the universe and power for underlying technology that makes the world better. It is far more powerful in these ways than any other approach, than religion, for example. And working with it and having the beauty of new understandings of the universe, the beauty of new technologies. People associated with me basically pioneered quantum technology, quantum sensing, things that are a big deal now in private companies. It's just fun. It's a huge amount of fun, and it really has an impact. So why would I do anything else?
You said to use technology to make the world better. How do you look at AI development today?
AI development is very early on, and there are lots of worries about it.
Doesn't look like.
And there's lots of worries about it, and it is a very powerful tool to make the world better. But there are lots of worries that it may make the world worse, and we just have to see. We have to move carefully, and so I think. But if you ask me what do I believe about its dangers, I say I don't know because I haven't studied it deeply enough, and I don't comment on things unless I have studied them deeply enough to have what I regard as a somewhat reliable opinion.
My last one question to you is, do you have any advice for, under all your experience, to our young viewers?
Well, one single advice that I have, it just deals with how you choose what to do in life. What to do for a profession, how to spend your time. And it's advice that I got from my grandfather when I was 4 years old. He put it in simple terms for a small child. He said, if you find a job when you grow up that is like play, you'll be a big success in life. And I came to understand that what he was really saying was that the things that are really worth doing are very difficult. They require that you work very hard in order to have success. And in order to work very hard, you have to enjoy what you're doing. And that then becomes an additional benefit, because if you enjoy what you're doing, then it helps make life worth living. And so I rather strongly believe that a young person, as they mature, as they go through university, if that's the direction they choose, as they move into some particular profession, or they choose what to do within some particular profession, watch for things that will be fun and worthwhile, but factor in the enjoyment part of it. That's very important towards success.
And my last one question, I promise. What was the Kip Thorne the most difficult decision in your career?
I don't think in the end that any of the decisions were terribly difficult. But they weren't terribly difficult because I studied the pros and the cons very carefully. And then it became fairly obvious what I wanted to do. But one decision that initially was very difficult was whether to pursue detection of gravitational waves, because I knew it was going to take decades. And And I knew it was so hard that it might be impossible to succeed. But I had to become convinced that you had a reasonable possibility of success. And once I was convinced of that, then the fact that the payoff would be so enormous swaying the decision. But it took me several years to make the decision, because it took me several years to become convinced that we had a serious possibility of success.
Thank you for your time.
Thank you.